In Chapter 4 of the methods text, we're going to expand on the solution methods that we studied in Chapter 3 to now apply them to methods for finding solutions to systems of both linear and nonlinear equations. This will include very large systems, and we'll discuss a feature of mathematical models called ill conditioning, and we'll develop numerical solution methods for systems of nonlinear equations. For a linear system of equations that is exactly specified, we might have n equations in n unknowns. The unknowns here are represented by the variables x1 through xn in the vector x. And the linear equations can be written in matrix and vector form this way, where A represents the coefficient matrix. The solution methods that we will study for solving linear systems include direct methods and indirect methods. You may already be familiar with methods like Gauss elimination, which is a direct method for solving linear systems. The direct methods use a predetermined number of operations. The indirect methods, on the other hand, are iterative methods. We may not know ahead of time how many iterations are required to reach convergence. As we will see, the indirect methods can be particularly useful for solving large systems of equations because they can reduce the total number of operations required compared to the direct methods. We'll begin with the direct methods, and we'll start with defining something called the augmented matrix for the linear system AX equals B. The augmented matrix has n rows and n plus 1 columns, where the vector B forms the last column. In Gauss elimination, we first transform the augmented matrix to an upper triangular matrix using what are called elementary row operations. All of the elementary row operations are linear operations. Elementary row operation 1 is to multiply any row in the augmented matrix by a non-zero constant. ERO2 is where we interchange two rows of a matrix. And ERO3 is where we multiply a row by a non-zero constant and add the result to a different row to replace the second row with the result. When doing ERO3, the row that we multiply and add is called the pivot row. To perform Gauss elimination, we convert the augmented matrix to an upper diagonal matrix by eliminating all of the non-zero elements below the first row in the first column and all of the non-zero elements below the second row in the second column, and all of the non-zero elements below the third row in the third column. That is, all of the elements below the diagonal of the matrix. The upper left-hand element of the augmented matrix, A11, is 0. Then we can use ERO2 to swap row 1 with a different row. But if A11 is non-zero, then we use the third elementary row operation and A11 as the pivot to eliminate A21 and A31. Then we use elementary row operation 3 again to eliminate all of the elements below A22. We continue eliminating all of the elements below the diagonal until we have an upper triangular matrix. This upper triangular matrix can then be solved from bottom to top by what we call back substitution. In this example, we have 3 rows and 4 columns in the augmented matrix. Regardless of the number of rows and columns, the very last row of the augmented matrix will always give us the last element of our unknown vector x directly. Once we know the last element of our unknown vector, we can substitute that into the second to last row to find the second to last unknown element, x2. Since Gauss elimination follows a prescribed pattern, it's straightforward to write a MATLAB script that will implement this method. Sometimes our pivot happens to be a very small non-zero number. When performing Gauss elimination using a small non-zero number as a pivot, this can result in round-off error. The Gauss elimination method can be improved by using what's called partial pivoting with row scaling. To implement partial pivoting with row scaling, we choose the row I in which AI1 is the largest relative to the other values in that row. And then we move that row that has the largest relative value of the first element to the top using elementary row operation 2, and we use this as the pivot row to eliminate all of the other elements in the first column of the augmented matrix. After performing the eliminations in the first column, we repeat the row scaling to eliminate all of the elements below the diagonal in the second column, all of the elements below the diagonal in the third column, etc. As we said before, the number of operations required for Gauss elimination is prescribed by the size of the augmented matrix. For a system with n unknowns, the augmented matrix is an n by n plus 1 matrix. At each step k in the Gauss elimination, we require n minus k division operations to find the multipliers for each row. And then there are a countable number of multiplications that are required to find the elements that get added to each of the n minus k rows. Finally, we have to perform the additions to find the new elements of the n minus k rows. The number of operations in the elimination steps, that is, the number of operations required to produce the upper triangular matrix for Gauss elimination, approaches 2/3 n cubed as n gets large. Then we must perform the back substitution operations to calculate each of the unknowns. This requires n minus k multiplications and n minus k subtractions for finding each unknown element x sub k, followed by a single division. The number of operations for back substitution is also countable and scales as n squared as n gets large. For large n, the number of back substitution operations is small compared to the number of elimination operations. So the total number of operations for large n is approximately 2/3 n cubed. The Thomas method is a modified version of Gauss elimination that is suitable for use with what are called tridiagonal matrices. Tridiagonal matrices have non-zero elements only on the diagonal, the superdiagonal, marked in green here, and the subdiagonal, marked in red. As we'll see later, we will frequently encounter tridiagonal matrices, for example when solving partial differential equations and boundary value problems numerically. In cases like this, Gauss elimination is not very efficient because a script written to perform Gauss elimination will attempt to eliminate elements below the diagonal that are already zero, and therefore it performs a lot of unnecessary calculations. The Thomas method, for which you can find a script in the methods text, is a simplified version of Gauss elimination that performs only the necessary operations to eliminate the elements on the lower diagonal during the elimination step. The Thomas method is very fast for tridiagonal systems compared to Gauss elimination, but it can only be used when the coefficient matrix is tridiagonal or can be written in this form. While the Gauss elimination and Thomas methods are straightforward and intuitive, they are not always the fastest or best methods for solving linear systems. In the next video, we'll introduce LU factorization methods.